In this video, we will look into how to use the statistical plotting tools in the Bidiomiter Lab software. We will use what we've learned in the first video of Training Module 2. The statistical features are found in the Image Tools menu under Measurements as shown in the video. Here, a list of different statistical plots is found. Furthermore, we will look into some of the functionalities from the Conversion menu as well. But before we start looking into the statistics, we need to define some regions in the images where we will plot image data from. We place some rows on different colors in the images. Then add some lines on one of the maze kernels. We make two crosses in the image, one on the blue background and one on yellow. Furthermore, we paint three different layers in the three different colors in the image of the leaf. Now we are ready to look into the plots. We go to Image Tools and then Measurements and start with the plot called Statistics. In the top of the plot window, we see that the initial settings displays information from the red and blue row. For the blue square number 1, we see the mean value in this region for each band in the image. In the same way, we see the mean value for the red square in each band. The statistic displayed can be changed to be, for example, the standard deviation, the minimum and maximum pixel value in the region, and so on. If you click on the table, it is possible to copy the information to clipboard. This essentially is the same as Ctrl-C. The data can be directly pasted into, for example, Excel or any other software for plotting or data analysis. Now, we change the input settings to be layers instead. We now get the statistics from the painted regions in the image of the leaf. Here again, the regions are defined and labeled with colors. The statistical information listed per band and color is then based only on the pixels painted with these three layers. Notice that statistics for regions in two different images can be shown at the same time. And also that this plot only shows data for shapes enclosing an area, therefore only rectangles, circles, and painted regions. Thus, we do not see information for the defined crosses and lines. Now we will move on and look into the histogram plot. Again, this plot only shows data for shapes enclosing an area, therefore only rectangles, circles, and painted regions. We start by looking at the two squared rows. In the plot, the x-axis is pixel values and the y-axis is the corresponding fraction. The plot can also be displayed as a line chart as shown in the video. For the blue curve showing pixel values from the maze, we see two peaks, one for the lighter yellow area and one for the darker yellow. The red curve describing the color in the leaf only has one major peak, as the color here is more homogeneous. Furthermore, it is possible to normalize and smooth the curve in the plot as well. As we saw with the statistics plot, we can also shift the data in the plot so it displays data for the painted layers. Now we see the three different colored peaks corresponding to three different colored areas in the leaf tip. A final remark, which is applicable for all the plots, is that the data displayed is band dependent. So, when you change the band number in the plotting tool, the pixel distribution for the different layers changes as well. For example, in band number 7 at wavelengths 515 nanometers, which is cyan, we see that the pixel values for the brown and yellow part of the leaf is more or less the same compared to the green leaf. Whereas in band 8, which is green light, the yellow leaf looks different from the brown and green part of the leaf. So with this tool, one can easily get an idea of in which bands we see the biggest difference between classes in the images. Now moving on to the profile plot. The profile plotting tool works only for lines. So, what is seen in the plot is the two lines drawn on the two axes of the maze kernel, again labeled by color. We select the blue line so that it is highlighted in the plot. The x-axis is number of pixels and y-axis is the pixel value. So for the blue line we observe that the pixel values are higher, thus a lighter color, in the top of the maze kernel, and gradually becomes darker towards the end of the kernel. As the x-axis is defined by the length of the line in pixels, one can also use this tool for measuring sizes in the images. In the bottom of the plot we can read of the length of the blue line, which is 10.9 millimeters long, Moreover, the angle with respect to the horizontal plane is given as well. For the yellow line, the profile shows how the edges of the maze kernel have a darker color, where the center part is lighter and have higher pixel values. We try to draw a line on the background, and again, in the profile we can see the small repeated peaks, which is the clearly defined light blue lines in the background. In general, the profiling tool is very useful for determining threshold values in the images. Now we will look into the spectrum plot. In this plot, the x-axis is wavelength and the y-axis pixel values. This plot works for regions enclosing an area, including rectangles, circles, the small crosses, and painted regions. So, what we are initially seeing in the plot is the two squares, the red and blue one, and then the two crosses, the green and pink one. On the lines in the plot, every dot is a band in the image with an associated pixel value. As a default, the pixel value is the mean for the defined row or layer. But as shown in the video, standard deviations can be added to the lines. For example, the red square has very little variation as it has a homogeneous green color, whereas the blue square on the maze has a larger variation due to the two different yellow colors. The small green and pink crosses have very little variation as well, as they are only defined by 9 pixels. If the images have been captured with additional filters, these can be added to the plot as well, as shown in the video. Furthermore, it is possible to normalize the plot, for example with respect to a specific band. This is done by clicking on the band you want to normalize with respect to, as shown in the video. Other normalization procedures are also available through this drop-down menu. The spectrum also works for painted layers, as mentioned earlier. From the plot, it is clear that the biggest visual difference for the 3 colors in the tip of the leaf lies in the visible spectrum, from around 500 nanometers to 700 nanometers, which is a color spectrum from green to red. In the bottom of the measurement menu, one finds the texture plot. The texture plot only works for regions defined by squares, thus in this case the red and blue square. In this plot, the x-axis is a zooming out scale running from 1 to 6 in this case. This zooming out is done with either a Gaussian or Laplacian pyramid. As you go up in levels in these pyramids, the level of visible detail will correspondingly go down. The y-axis is dependent on the descriptor chosen for the plot. If we, for example, as a starting point, look at the red square on the leaf and zoom in, we see a lot of detail in the leaf. But when we then zoom out, the level of detail gradually becomes less, and this is what is reflected by the decreasing trend in the plot. The y-axis can be changed to be dependent on different descriptors, for example the mean or correlation among others. The standard default descriptor is the standard deviation. As with the other plots, normalization can also be turned on and off. The last plot we will be looking at is called a density plot. This plot only works for painted layers. The intention with this plot is to visualize the similarity of difference within the bands for different painted classes. Initially, as seen in the video, a comparison of band 1 and 2 is performed. Press Update to display the information. After pressing Update, 3 colorful clouds appear in the plot. Each of the individual points in the plot has a coordinate, where the x-axis is the pixel value in the x-axis band, and the y-coordinate is the corresponding pixel value in the y-axis band. So essentially this means that if the pixels have the same value in the 2 bands which are compared, one will see a linear trend in the point cloud in the diagonal of the plot. When the bands compared are changed, as seen in the video, the location of the different colored clouds change, not only in the plot but also relative to each other. This tool can thus be used to identify among which bands we find the biggest difference between certain classes and colors. For now, we will leave the plots and move on to the conversion menu. Under Extract Bands, a small window as the one seen in the video will pop up. From this menu, it is possible to extract a limited specific number of bands to a new image or several individual image bands. Under CLab, you can convert your image into the CLab color space. CLab is a 3-dimensional color space, just like their RGB color space. When you convert your image to CLab, the image conversion will only contain 3 bands, 1 for each of these dimensions. Moreover, the image band can also be converted into RGB images, where a selection of different tones is available. As seen in the video, the D50 Sunset Daylight option is chosen, and the resulting image has a warmer tone to it. Then there is a feature called reflectance to absorbance. Normally, when taking an image, the camera creates the image based on the reflected light from the sample, but it is also possible to visualize the image from the absorbed light. To get any meaningful result out of this conversion, change the view mode to grayscale and scroll through the bands as done in the video. In the video is seen a comparison for the leaf image in band 9 for the absorbance versus the reflectance. Now we have seen how to extract statistical information from the images and plot it with different plotting tools. We have seen the statistics plot, a histogram, a profile, the spectrum plot, texture plot, and density plot. We have gone through the conversion menu and illustrated how to visualize different color spaces and illustrate images by absorbance.